Okay, this is part 2 of our lecture on chapter 2. And we're going to talk about gravity. We'll talk about setting up some problems. We'll watch a video and then we'll do an example problem. So objects falling under the influence of gravity are an example of motion with a uniform acceleration. A freely falling object is any object moving freely under the influence of gravity alone. So we are neglecting drag in this case. Near the surface of the Earth, Galileo discovered that all objects experience approximately the same acceleration of gravity. And when he discovered this, it wasn't obvious that all objects experience the same acceleration of gravity. The direction of acceleration of an object in free fall is directed downward, regardless of the initial motion. So the magnitude of acceleration of gravity is 9.8 meters per second squared. It's directed downward, so it's a vector, points down towards the center of the Earth or just down vertically. In reality, g isn't the same everywhere, so g decreases with increasing altitude. So the further we get away from the Earth, the g decreases. G also varies with latitude. And so the value that we use, 9.8 meters per second squared, is the average close to the Earth's surface. So we're going to watch this video. So this is a video from the last Apollo 15 moonwalk. Commander David Scott performed a live demonstration for the TV. He held out a geologic hammer and a feather, and he dropped them at the same time because they were in a vacuum, basically. On the moon, there was no air resistance, and the feather and the hammer fell at the same rate. And so this shows Galileo's finding that all objects released together fall at the same rate regardless of mass. So let's watch this.
Tim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
Superb.
Okay. So setting up kinematic problems, we're working with one-dimensional motion. So everything that we talk about here is going to be one-dimensional motion. And in chapter 4, we'll start talking about two-dimensional motion. And chapter 3, we'll start talking about vectors. But for now, we want to orient everything, our object that's moving along one direction so that we can use the simplicity of one-dimensional motion. So in this example, this is a car, and the car is moving to the right in the positive x direction. And so that's one-dimensional motion in the x direction. So when we're setting up the problem, we are looking for our givens and our finds. And so usually we're given, we could be given the starting position and maybe the final position. We're given sometimes the starting velocity or the final velocity and the starting time or the ending time. And we may be given the acceleration of gravity. So all of these variables we could be given, or we need to find them using the kinematic equations that we talked about in the last part 1 of the lecture. So that was the x direction, and this is the y direction. So when we drop this apple, right, this is an example of a motion map. And when we drop the apple, we can see that the location, right, these is separated in time by the same increment in time. So we've got, let's say, for example, maybe 1 second between the start and the next apple, and then 1 second and 1 second and 1 second. And we can see that the displacement is increasing as the apple falls. And so on this problem, we might be given, or we have to find these variables. So initial y value and final y value, initial y value for velocity, or the acceleration in the y direction. And in this case, when we're talking about free fall, that ay would just be g. And then we also have the example of an object on an incline. And so we've got a ramp here, right? And what we do is we take our coordinate system and we rotate it up so that down the ramp is considered our x direction. And that x direction down the ramp is the 1D motion that we're going to be talking about. And so when we talk about gravity, we know gravity is down, but we can find the component of gravity that's in the x direction. And so this would be the component of gravity in the x direction, and that's just given by g sine theta. So that's what we would write here. We would write g sine theta in this spot, and then we would be given values of maybe the start position down on this ramp along this coordinate, the final position, the velocity down the ramp, and so on. And so these are just the three kind of common examples that we see where we're using one-dimensional motion. Okay, so we're going to do a whiteboard problem. So let me pull up my camera here. Okay, so we have this baseball directed. We throw a baseball directly upward at time t equals 0. And we have an initial speed of 12.3 meters per second. We're asked, what is the maximum height the ball reaches above where it leaves your hand? And at what time does the ball pass through half the maximum height? And we're going to ignore air resistance or drag, and we're going to assume that gravity is 9.8 meters per second squared. So the first thing I'm going to do using my problem-solving strategy is I'm going to say that my hand that I'm going to throw the ball at is going to be at x equals 0. So this is going to be x equals 0. And my final height is going to be somewhere up here. So let me draw my motion map. So I start out with a velocity, say like this. Right? And I know that my velocity is decreasing because my acceleration is down. So this is my next ball. And then I have a shorter velocity arrow and a shorter velocity arrow. And then the shortest velocity arrow, something like that. Okay, and so I know that my initial velocity here, this is going to be my v initial, is equal to 12.3 meters per second. And I know g is going to equal, so my a equals g, which is equal to 9.8 meters per second squared. Okay, make sure to get my units right. And now I'm going to go through givens and finds. So even though I drew them on my picture, I'm going to write them over here also. So I'm given that g is equal to 9.8 meters per second squared. I'm also given that the initial velocity that the ball is thrown up with is 12.3 meters per second. The other thing, I know that when the ball reaches its final height right here, I know that my velocity is equal to 0. So I'm going to say v final is equal to 0. And I want to find the delta y. So I want to find this from here to here. So if we call this, let's instead of x, let's call this y. Y equals 0, and y is equal to y final up here, yf. So I want to find y final. And I also want to find the time t that is 1/2 of the final height, right? So t half, let's call it, or let's just call it t for now. So t means that when I get here, so at half the value, say this spot is 1/2 y final. I want to know how long that takes to get to y final. So that t. All right, so the first thing I'm going to do is I'm going to find y final, and I'm going to use the equation from kinematics. Let's see if I go back here to my kinematic equations, and let me just pause this for a second. All right, I'm going to use this bottom equation right here. So I'm going to use this equation right here. V final squared is equal to V initial squared plus 2a and this is delta x final minus the x initial. So that's what I'll be using. Let's go back. And let's see if I can make this bigger. There we go. Okay, so I'm going to use v final squared is equal to v initial squared plus 2a delta y. And so delta y is from here to here. Okay, and so that's going to equal, so v final squared is equal to v initial squared plus 2 times minus g, right? My acceleration is down, but my velocity is up. So my g is going to be in the negative direction, and this is going to be y final minus y initial. And I know my y initial, I set that equal to 0 here. So I'm going to set this equal to 0. And I know that my v final here is going to equal 0. So how do I know that? Well, I'm throwing the ball up, and when it reaches this point right here for 1 instant in time, the velocity, we can tell from the arrows, they get shorter and shorter. And right there, the velocity is equal to 0. And then it starts to head back down. So I actually didn't draw that. So this is going up, and then this is going down. All right, so and like that. And so it slows down going up, and it increases in speed going back down. Okay, so this is going to equal 0, and I'm solving for y final. That's what I want to know. So I'm going to rewrite this equation. So 0 is equal to v initial squared minus 2g times y final. So what I'm trying to find. So I'm going to bring this term over to the other side. I'm going to add 2g y final to both sides. So 2g y final is equal to v initial squared. And now I'm going to solve for y final, so I divide both sides by 2g. And I get y final is equal to v initial squared over to 2g. And when I plug that in, my v initial squared from my givens here is 12.3 meters per second squared over 2 times 9.8 meters per second. And I'm going to find that. I'm going to use my MATLAB to do that. If it comes back up for me. There we go. See if I can just put that off to the side. Okay, so what I want here is I'm going to actually use my variables. So I'm going to say my v initial is equal to 12.3. And I'm going to say my acceleration is equal to 9.8. And so now I can write my v final is equal to v initial squared divided by 2 times gravity. And I get, right, I used G instead of A. So I'm just going to fix that, make that A. And I get 7.72. So y final is 7.72 meters. See that over here? Okay, and so the next thing so this is my answer, my y final. I'm looking for y final 7.72. And now what I want to do is I want to find the time that it takes for it to get to half the height. So halfway up. So I'm looking for, so let's say y final is equal to 7.72 meters. And so now I'm going to do the next part, and I'm going to try to find my delta t. So I'm going to use this equation. Let's go back over here. I'm going to use this equation. This x final is equal to x initial plus v naught t plus 1/2 at squared. So that's what I'm going to use. And let me pull back up my MATLAB. If I can get there from the, there it is. Okay, there we are. So I'm going to say here, x final is equal to x initial. And actually I want to use the y values, right? So I'm going to use y final is equal to y initial plus v naught times t plus 1/2 a t squared. And so I want to figure out what can I get rid of here? Well, I know in my picture that I set the initial value for y at y equals 0. So I'm going to be able to cancel that out of my equation here. So this is going to go to 0. I know my v initial is 12.3. So I'm going to write this out. So I'm going to say y final. So y final is equal to 12.3 times t plus 1/2 times minus g times t squared. Okay, and now for what do I want to put for y final? Well, I really don't want y final. I want to know the time it takes to go halfway. So I'm actually going to change this to say y final over 2 and y final over 2. So I get y final over 2. So this is going to be 7.72 over 2 is equal to 12.3 t minus 1/2 times 9.8 times t squared. And now this looks like a quadratic equation to me. So I'm going to write it in quadratic equation form. And so that means that I'm going to write it as a t squared plus bt plus c is equal to 0. And then I'm going to use the solution for the quadratic equation is t is equal to a negative b plus or minus b squared minus 4ac square root over 2a. Okay, so let's figure out what we have here. So for a, we have 9.8 divided by 2, and it's a negative. So I'm going to have a negative 9.8 divided by 2 is 4.9 t squared, and I'm going to have plus 12.3 t, and minus 7.72 is 3.6, no, 3.5. 8. Let's see, 3.9, something like that. 81, 9, 851. Or we'll just leave it as 7.72 because I'm not able to do this math in my head right at the moment, and that's equal to 0. So the next thing I'm going to do is just to simplify it is I'm going to multiply through by a negative. So I'm going to have 4.9 t squared minus 12.3 t plus 7.72 over 2 is equal to 0. So this is going to be my A, this is going to be my B, the whole thing is going to be my B, and this is going to be my C. And so I'm going to use MATLAB to figure it out. So I'm going to say A is equal to 4.9, B is equal to 12.3, and C is equal to 7.72 divided by 2. And if I put semicolons after these like this, it's not going to print. Just like up here, I didn't put a semicolon and it printed the answer. Here, it doesn't because I added the semicolons. So, but I've put the values in here. So, and I can tell I've put the values in here because I can see them over here. So I've got the values stored in MATLAB. Okay, so now if I want to find t, I'm just going to say t is equal to a negative b plus square root of b squared minus 4 times a times c, all divided by 2 times a. And I need to add in parentheses here because the whole thing needs to be divided by 2a, not just that square root term. And so I get a negative 3.64. And now if I do the same thing and I say a negative b minus, I get a negative 2.14. Both answers are negative, so that's a problem. Oh, I see. I think I see my problem. So here in my problem, I didn't keep the negative. So this is a negative 12.3. Okay, and now if I go and run this again, yeah. All right, so my answer here, I might have two answers. So one answer is t is equal to 2.14. seconds. And then let's try the other one. It's going to be a negative 0.36. And if we look back at our example here, whoops, wrong paper. If I look back at our example, there are 2 times when the ball is going to reach half the height. So it's either going to be at 0.3677 seconds or 2 on the back coming back down 2.1425 seconds. So because the problem, let's just look back at the problem and see what we have. So I think it specifies and it doesn't really say. It says at what time does the ball pass through half the maximum height, and so we'll just assume it's on the way up. So we're going to assume that our time here is t is equal to, I think it was 0.3677. Yeah, 0.38 seconds. So that's going to be the time for it to get halfway to the maximum height. And that's all we have for this chapter. And we'll cover more problems during class.